This is ECE 343, Signals and Systems. This is the first part of Chapter 2. So in Chapter 1, we introduced the concepts of signals and systems. We looked at their representation and some of their properties. One of the distinctions we saw with both signals and systems was this idea of continuous time and discrete time. Continuous time signals and systems requires fundamentally different mathematics than discrete time signals and systems. So throughout the rest of the book, you'll see that chapters will toggle back and forth between continuous time and discrete time treatments. So chapter 2 really is starting our process out of looking deeper into signals and systems, their interaction, and how we can describe and solve them. And it does so for continuous time systems. So this particular chapter is looking at the time domain analysis of continuous time systems. Later on, we will look at a frequency domain or transform domain analysis of continuous time systems as well. The primary way we are going to look at continuous time systems in this class is a class of systems that are called constant coefficient linear differential equations, CCLDEs, if you will. If we just break that up a little bit, the constant coefficient really is just code word for time invariant, one of the properties we talked back in chapter 1. Time invariance is one of those fundamental properties that's going to give us some really good advantages in trying to understand input-output behavior. Linear is exactly what it sounds. It's linearity. And differential equations, because differential equations can only operate on continuous time signals, we recognize that differential equations is appropriate for systems and signals that are continuous time. So when we take a look at continuous time systems as described by constant coefficient linear differential equations, we're really looking at what are called linear time invariant continuous systems. We're going to see this quite a bit, and so we're going to abbreviate that. We're going to call it LTIC systems. So let's take a look at what a constant coefficient linear differential equation looks like in general. I'm going to provide a standard form constant coefficient linear differential equation in expanded form. And if you take a look at the equation here, it starts out with a polynomial operator in the operator d, the derivative operator. And it starts out with a d to the n plus some a1 d to the n minus 1 plus going all the way down where we're decreasing the powers of the derivative operator until we get to just a constant an. That whole thing then is going to be operating on the output y of n. That's the left-hand side of the equation. On the right-hand side, we see something very similar. It's just the highest power of d now could be a different value. It could be a value m rather than a value n. And we're going to use different coefficients. So b0 d to the m plus b1 d to the m minus 1, going all the way down until we get to the constant term b sub m. This thing is going to be acting on the input x of t. So we do get an equation here, right? There's an equal sign in the middle. The coefficients, all the little a's and all the little b's are not a functions of time, so they are constant coefficient. We're just talking sums and scales of derivatives acting on things. That's the linearity part, linearity superposition, so summing and scaling. And it's a differential equation. It's involving derivatives. One quick note on this standard form constant coefficient linear differential equation is that the highest power or highest order of that derivative operator acting on the output variable, the coefficient there is generally normalized to 1. We would normally think of that as being a coefficient a sub 0. We're just going to set a sub 0 equal to 1. If you had a differential equation that did not have a sub 0 equaling to 1, you would just divide the entire equation by whatever that non-unity value a sub 0 is, and that would end up giving you that normalized a0 equaling 1 coefficient. It does get a little bit tedious to always drag along that whole polynomial, so we can also adopt a shorthand notation. QD is just a brief representation. Q is a polynomial in the operator D, which is defined as d to the n plus a1 d to the n minus 1 plus going all the way down to an. In a similar way, we can use a shorthand notation for that polynomial operator acting on the input x. We'll call that P of d, and that's just going to be defined as b0 d to the m all the way down to b sub m. So what can we get out of this? We can come up with a compact representation of these constant coefficient linear differential equations as qd acting on y of t equaling pd acting on x of t. Okay, So what do we want to do with all of this? This thing is an equation, obviously, and it describes our linear time invariant continuous system, and it does so by showing how the output y is related to the input x. So this is a system description. And the probably most obvious question on this is, how do we solve this thing? This class is very interested in making sure that we can break systems down and understand their behaviors so that we can understand the functionality between the functionality of the system and the relationship between the input and output. So how do you solve this? One of the prereqs for this class, obviously, is the math sequence. In the math sequence, you took a differential equation class, so you really should have seen the solution to differential equations like this. My guess is that many people in the class will not remember all the details on that, although you probably remember some language and terminology in there. These types of differential equations, most likely your differential equation class broke up the solution into a couple of pieces. They do that because solving these things is a little bit hard. It's a difficult task to solve a differential equation, especially all in one step. And if we break it up into simpler pieces, that aids in our ability to solve these guys. And at least in most differential equation classes, they break it up into what is called homogeneous and non-homogeneous components. For us as engineers, that homogeneous and non-homogeneous components is fine, but it's probably not as intuitive as a different way of breaking it up. So at least for this class, we're going to take a little bit different technique, or we're going to take a little bit different tact than what they did in differential equations. We're going to break it up according to what kind of output comes from what kind of energy. So there's really two possible sources of energy that can generate output on an equation like this, on a continuous time system. One is that there could already be energy in the system. So think of a circuit that has a resistor, capacitor, inductor kind of combination. Inductors and capacitors can hold energy, right? So there could be energy stored in that system, even without applying an external, let's say, function generator. So those internal sources of energy, a charged capacitor or a current running through an inductor, can produce an output even if we aren't externally applying an input. That particular kind of output we are going to call as the zero input response. So we're not looking at an externally applied input. We're only looking at what happens with internal energy and how it manifests itself. In a similar kind of way, we could ignore all of that energy on the inside. We could assume it was all equal to zero. That's a condition called zero state. When we talk about the state of a system, we're usually talking about the state of energy inside the system. So the state is set to zero, no internal energy, and then we apply an external input and we see what comes out on that. That particular kind of output coming from an input, but having the internal energy set equal to zero, the zero state, is called the zero state response. Those are the only two ways we can get output on these kind of systems, either internal energy already there, or applying energy through our input port. And because the system is linear, we know that if we can solve each of those two pieces separately, we can get the total response by adding them. So one of the things we'll just notice is that the total solution to our differential equation can be thought of as what is called the zero input response, right? Plus the zero state response. So this ZIR stands for zero input response, right? That zero input response means that the initial conditions, the initial energy, the energy inside the system, the initial conditions, which we'll start abbreviating ICs, right? The ICs of the system are driving the output, And then if I look at the ZSR, that's the zero state response, because it's in zero state, all the ICs are equal to zero. And really in this particular case, the input drives the response. Those are the only two different ways to get an output out of the system. Because it's linear, we can deal with each one of those separately. Let's just summarize that really quickly. Y zero input response T is the response, right? Is the response to initial conditions when, right? the input x of t equals 0. Y0 state response of t is the response, right, to the input x of t when the initial conditions are equal to 0. So internal energy equal to 0 and apply the energy through the input, something along those lines. So back to our solution. We have a differential equation, QD, acting on y of t being equal to PD acting on x of t. And we know that the solution to this, the solution can be expressed, right? It can be expressed as yt being equal to y0 input response of t plus y0 state response of t. So while it might not be total obvious at the current juncture, again, the reason we do this, number one, it's intuitive to look at the response to separate sources of energy, and also the math required for the solution, as we will see shortly. The math required to find YZIR or YZSR are different, and so we would like to be able to split them up so that we can apply those different math techniques to each. Let me do a quick aside, though, and talk about why this differential equation is kind of hard to solve in the first place. So I'm going to look at a very, very simple differential equation. I'm going to look at a first order differential equation, and we'll just look at this one in brief. In a brief sense. So I'm going to look at this one. I'm going to look at d plus 1 acting on y of t being equal to x of t. Some comments about this system. This is a first order system. How do I know that? The highest power of d, right? The highest power of d acting on y. That means the highest power of d in that polynomial qd, right? Tells us the system order. Tells us the system order. If this was an equation that derived from an electric circuit, that highest order would also tell me the number of energy storage elements in there. So a first order differential equation would only have a single energy storage element. It could have a single capacitor, or it could have a single inductor. It wouldn't have both, and it wouldn't have two capacitors. If you have separate energy storage elements in a circuit, they'll each contribute a D, and we know that through the ideal voltage current laws that are associated with both inductors and capacitors. So the highest power here tells us the order of the system. In this case, it's a first order system. I have an input. We generally know the input, right? We know if we turn a light switch on it or hook up a battery or put in a sinusoid or whatever the thing is that we drive the system with. We usually know that. What we're trying to find is the y of t. So let me get it out of operator form in this case, and let me instead just draw it in maybe something a little closer to what we saw in differential equations. I'm going to do this as a y dot of t, right, plus y of t being equal to x of t. And I want to solve for y of t, right? I guess you could sit there and look at it and say, oh, I see that one y of t, so let me just put that y of t on the left and put everything else on the right. So I get y of t equals minus y dot of t plus x of t, something like that. Does that really help us, though? I'm going to suggest that doesn't really help us much at all, right? Because I have an equation for y, but it's got y's on the right-hand side, right? There is that y on the right-hand side. And if I don't know that y on the left, I'm certainly not going to be able to get it by putting it in terms of itself, something that I don't know. So I can't just do this by kind of doing a superficial solution by putting y equals something that's a function of y. I need y all by itself on the left-hand side, okay? So to solve, to solve, I need y of t equals something, right? Something without y's, right? Okay, so we go back to the equation. We look at this guy again. So I have y dot of t plus y of t equaling x of t, and I need to somehow get y by itself. I think one of our natural approaches is to try to think about this in an algebraic sense, and so I want to get that y by itself. But I've got a problem, right? Because there's this y and it has a y dot, and that derivative is stuck to the variable of interest. There's really no easy way in the time domain to break that dot away from the y and allow us to algebraically solve for y, okay? So we can't separate in this case, right? We can't separate. We can't separate. At least in the time domain, we can't. For those of you who remember your Laplace transforms and transform domain analysis, one of the reasons we like that so much is because it does allow separation of the derivative from the variable of interest, so you can solve it algebraically. That's really one of the driving forces as to why transform domain is so nice. We're not up to transform domain, we're doing time domain analysis. So in the time domain, we can't separate in the time domain, right, the derivative from the variable, right? And what does that tell us? No way to solve algebraically. Algebraically. That might not be the right spelling of algebraically. So let's just get rid of that. And we will say to solve with algebra. How about that? Algebra. So we're not going to be able to solve this guy with algebra. Okay, so we know an algebraic solution isn't possible. We're going to need something more sophisticated. We're going to need to be able to deal with that fact that that derivative is stuck to the variable of interest. And that turns out not to be the most trivial thing in the time domain. Okay, so let's go back to what we had looked at as a decomposition of that solution. Remember, we are trying to find QD acting on y of t being equal to PD acting on x of t. And we know that the total solution on there can be thought of in terms of output in response to different sources of energy, so internally stored energy or externally applied energy. The zero input or zero state responses both capture those guys. And so I've got two pieces. I've got to start with something. I've got to figure out which one of these two pieces I want to deal with. And what I'm going to suggest is that we are going to want to do the zero input response first, and then we're going to do the zero state response second. The zero input response is a logical starting point. Why? Because this guy sets x of t equaling to 0. Think about what that does to your equation. This whole right-hand side of the equation will go to 0 for the zero input response, right? That gets rid of half the complexity of the equation. So at least on a quick glance of this, it would seem likely that the zero input response is going to be a simpler task to solve, and it turns out it is. And we can also use what we learned from the zero input response to help drive part of our solution to the zero state response. So this is the approach we'll take. We're going to go ahead and look at the zero input response first. So in this particular case, we're going to focus on. So let's focus first on the y zero input response of t. What does that mean I need to do? I'm wanting to solve the equation QD acting on y of t being equal to 0. That's the thing that I want to be able to solve. And recall, since y of t equals 0, or not y of t, x of t, the input is equal to 0. Since x of t equals to 0, the output y of t is driven, it's driven by initial conditions, energy stored in the system. Another thing to consider in this, QD, right, that polynomial operator in D, we said the order of the system depended on the highest order derivative in Q. We looked at a first order case before, you could have whatever order. We said that those were all energy storage elements, right? All of those energy storage elements, right, can support an initial condition. If I have a second order system that has a capacitor and an inductor, for example, the capacitor can have an initial voltage, right, and the inductor can have an initial current. So two initial conditions for that circuit with two energy storage elements. We find all of these things connected. So Q, the polynomial operator acting on our output Y, the highest power of D is the order of the system, and that order of the system corresponds to the number of energy storage elements, and it's also going to correspond to the number of initial conditions that the circuit or system can support. So when I think about what is or how do I find, so how to find the solution here, the solution Y zero input response of t to this guy, I think that maybe a way that we can approach this is to look at a simple example. So let's consider let's look at a first order example. Okay, in this first order example, I'm just going to write it out in expanded form. We're going to have a d. I normalize that highest power of d coefficient to 1, so I'm going to get d, and then I'm going to have a plus some a1, no d there because I just decreased the power of d, so it's a simple d plus a1, acting on y zir of t, and set that equal to 0. If I rewrite that just a little bit, right, that's going to be a y dot zir of t being equal to minus a1 y zir of t. So I'm looking for a signal, a solution, y, right, such that it's equal to a scale of its own derivative, or conversely, that the derivative is equal to a scale of the signal. What kind of signal is equal to its own derivative? You should know from calculus that really there's only one kind of signal that's equal to its own derivative, and that is this idea of an exponential. So only an exponential has this property of the derivative being equal to a scale of itself. Okay, so we will hypothesize that the solution y zir of t takes the form of an exponential. It could have some scale factor up front. I'll call that c e to the lambda t. So I'm just going to assume that this guy can take the form of an exponential. So let's go ahead and substitute this guy. Let's sub our y zir of t into the equation and see if it works. So what were we looking at? We said that the equation was d plus a1 acting on y zir of t being equal to 0. And we're going to do this for y zir of t equaling c e to the lambda t. So I'm going to go ahead and plug that in there. So I'm going to have a d plus a1 acting on c e to the lambda t, right, being equal to 0. I'm going to go ahead and do the derivative of c e to the lambda t. I know what that is. That's going to be a c lambda e to the lambda t. And then I add to that a1 times that c e to the lambda t. That's pretty easy. That's c a1 e to the lambda t. And we're wondering if we can force that equal to 0. I'm going to do a little bit of algebra here. I'm going to pull the c out front. So I'm going to have a c, and then I'm going to have a lambda plus a1, and I'm going to have an e to the lambda t, and we're looking to see if we can force that equal to 0. So some things to think about. Can we get to 0, right, by that parameter c? Sure, I could put c equal to 0 and I could make this thing work. But what would that tell me? That would tell me, right, that my solution was 0. That's not going to be too interesting, right? Setting c equaling to 0, it does satisfy the equation, but it's a trivial solution. It's just saying the output's nothing. So really, this is not something that is going to help me. So that doesn't help me in a useful way. If I look at this function e to the lambda t, I don't care what constant lambda you put in there. There is no way that I can make e to the lambda t be equal to 0, right, for all different time. So that doesn't help us get to the 0. The only thing that really allows me to get to 0 is if I have lambda plus a1 equaling to 0. This guy can help me. So if lambda plus a1 equaling to 0, right, which implies what? That lambda equals minus a1, then, right, then my y zirt equaling to c e to the lambda t works as a solution. What does that mean? That means my hypothesis was correct, but it requires a particular form. It requires a particular shape. And that shape comes from my original polynomial q, because it depends. The lambda of my solution, right, depends on those coefficients a that were in my original differential equation. So what do we get out of all of this? We can say y zir of t is equal to some c e to the, well, what is lambda in this case? It's going to be lambda t, or say c equaling c e to the minus a1t, that those guys work, right? Those guys work. For lots of reasons, we will go ahead and we will utilize this notation lambda. We're going to call these guys the characteristic roots of our system, the characteristic root of the system, okay? So we need a connection to the system itself that's going to tell us something about the shape of the exponentials that can come out as released by the system when you stuff energy internally in the system. So we know it's going to be exponential form, and we know that the shape of that exponential, which depends on lambda, comes from that q, something along those lines. All of that is known, right? So this stuff over here is known from our q. Okay, we can figure out what kinds of exponentials our system are going to support just by looking at the coefficients of the differential equation, and in particular, the coefficients of that q polynomial. The thing that's left then is the c. So how do we get the scale factor? The scale factor c, right? How do we get that scale factor? If you think about it, our solution here scales directly with c. So there should be cases when you're always going to get the exponential. You can't change that shape. That's connected to the underlying differential equation form. But there could be different scale factors here that work, and that should make sense. If I dump twice as much energy into a system, right? If I put twice as much voltage on the capacitor, or I put twice as much current through an inductor, I would expect that the solution, right, the way that the output comes on that would double as well. It's a linear system after all, right? So there's something about this C that probably should be connected to the amount of energy that we stick into the system, right? And it turns out this is correct. We solve for the C. We find the C from, that's not quite right. We get it from the initial conditions, okay? So a nth order differential equation would have n initial conditions, and we end up using those initial conditions to find these coefficients that weight the overall exponentials that make up this y, z, I, r of t. Okay, so what have we done at this point? I've looked at a first order differential equation, and I'm looking for the zero input response. We looked at what condition would be required for us to get a solution. It required that the solution be equal to its own derivative, and we know only an exponential can be that. So we went ahead and hypothesized the zero input response was an exponential, and we stuffed it back into the differential equation, and we saw it could, as long as that exponential had a shape as dictated by the q. That left one unknown in that first order case, the c's, which would come from the initial conditions. So I think we can generalize now. We're going to go ahead and generalize. Let's generalize. We can generalize this idea. We're going to use something like a ce to the lambda t, right, in a overall generic qd y of t being equal to 0. Okay, we're going to see if an exponential works not just in the first order case, but in an nth order case. What do we get in here? What is qd? Qd looks like this. It's d to the n plus some a1 d to the n minus 1 plus going all the way down to an an. We are going to be having that operate on our hypothesized solution, ce to the lambda t, set it equal to 0. Well, this is a pretty easy set of operations to do. The whatever derivative it is acting on ce to the lambda t just brings lambda down, whatever the order of the derivative is, okay? So d to the n, right, ce to the lambda t would give me a lambda to the n, and we'd still have that ce to the lambda t, okay? The a1 d to the n minus 1 acting on ce to the lambda t would give me an a1 lambda to the n minus 1 times c e to the lambda t. So I can get in here an a1 lambda to the n minus 1. And we're going to keep going down there all the way down to an. So if I use this hypothesized exponential, right, as a solution to this guy, and just go through the derivative operations, what do I find? I find that I get q now not of d, but of lambda, just some constant, right? Q of lambda times c e to the lambda t being equal to 0. This is the thing we need to check. For the same reasons we talked before, setting c equaling to 0 is boring and not something we're interested in. That just makes the whole output equal to 0, not a useful one. The e to the lambda t cannot be 0 for all time, so that doesn't help us get to 0. But this q of lambda can. This is how we get to 0. This helps us. This helps get us to 0. Get us to 0. And how does it do it? We need q of lambda be equal to 0. And what does that require? That requires a lambda to the n plus some a1 lambda to the n minus 1 plus going all the way down to some a to the n equaling to 0. Is there a way you can make a polynomial, an nth order polynomial, equal to 0? Sure, right? There are n roots, right? That means there's n values of lambda where this happens. So what does that mean? That means that if I count those guys up, if I go lambda 1 all the way out to lambda n, are all possible solutions. So for an nth order differential equation that has that nth order polynomial in D, we find out that an exponential can solve that zero input response with n different exponentials as dictated by this lambda 1 through lambda n, which comes from that setting that q lambda, right, that q lambda equaling to 0, something along those lines. Okay, so because the system is linear, and because e to the lambda t works, right, for lambda equaling lambda 1 or lambda 2 all the way out to lambda n, any linear combination, any linear combo of these terms works. This is tedious to show. It's not hard, it's just tedious. And I'll leave it to you if you want to go beyond a first order solution and plug it back in the differential equation and verify it works. It's tedious, but not terribly difficult to do. Any linear combination of these terms works as a solution, which means what? It means that our y ZIR of t will look something like, right, a c1 e to the lambda 1 t plus all the way down to a cn e to the lambda n t. Okay, we get the lambda i's, if you will, from this q lambda equaling 0, right? And we get the ci's from our initial conditions. I will put a little caveat on this. I've played one small quick one, I guess, on this, is that this form up here, this assumes that the lambda i's are unique. If you have repeated roots, and we talked a little bit about some issues with repeated roots before. If you have repeated roots, you're going to have to change, or repeated terms. Those repeated terms are going to require just a little modification to the process, just like repeated factors in a partial fraction expansion required a little modification to their process. Right now, we're just trying to get the basic idea. And what do we find? We find that an nth order differential equation, when we're looking for the zero input response, has exponentials that are the solution because it's a linear system. Any linear combination of the potential exponentials is our overall solution. There are n exponentials which can be solved into that nth order differential equation. We can get the lambdas directly from the differential equation polynomial Q, so those are known, and we get the CIs from whatever initial condition states are on our differential equation. Let's put in just a little bit of terminology, okay? So some terminology. Q of lambda is called what? This is called the characteristic polynomial. Why do they call it the characteristic polynomial? Because it has embedded into it the character of the system. The different Q's are going to give us different lambdas when we solve it, right? And those different lambdas tell us the different shape exponentials that this system wants to release energy for. And I'll try to give an example of that in a minute. So because Q dictates what kind of shape comes out of this, how the system wants to release energy, something about its fundamental character, this polynomial Q, which helps us get that, is called the characteristic polynomial. If I set Q lambda equaling to 0, this thing is called the characteristic equation. Characteristic equation. If we solve that, solve and get our lambda i's, those guys are called the characteristic roots. And I think the reason there is pretty obvious. It's the roots of that polynomial, characteristic roots. And these characteristic roots, right, tell us something about the characteristics of the system, the character of the system. The e to the lambda i's, these guys are called the characteristic modes. Characteristic modes. Characteristic modes, this is the way a system wants to release energy, okay? So if I was going to look at this guy, maybe I would just note that a constant coefficient linear differential equation releases, right? It releases stored energy. Stored energy. Dang, come on. It releases stored energy in the form of a characteristic or combination of characteristic mode or modes, right? It has no other choice. There's no other way this linear time invariant continuous system as described by this constant coefficient linear differential equation can release energy. It has to release energy, right? It has to release energy in exponential forms. We had mentioned back in the background chapter that understanding of exponentials was crucial to this class. You have to be able to understand exponentials. This is really our first tangible understanding or kind of confirmation that that's the case. When we look at this huge class of systems, which you've actually studied quite a bit back in circuits, those described by a constant coefficient linear differential equation, we see now that the way that these systems want to release energy is always in exponential form. Now, the shape of that exponential depends a little bit. It depends on that Q. Different polynomial Qs give you different characteristic roots, lambda, and those characteristic root lambda, right, change how the output can look. So, for example, consider two first-order systems. So let's look at two first-order systems, something like that. I'm going to have one that is going to be a d plus 1, y being equal to, let's call it x, and the other one's going to be a d plus 2, y equaling x, something like that. If I look at this first one, right, what is the q? Q, right, of, let's make it of lambda. We just replace d with lambda. That's going to be lambda plus 1. If I set that equal to 0, that's the characteristic equation. Solve that guy. I get lambda equaling minus 1. That tells me the characteristic root. And if I put that characteristic root into exponential form, I get an e to the minus t. That is my characteristic mode, right? That tells me how this system wants to release energy. If I take a look at that guy, it's an exponential kind of decay, something like that. It decays as e to the minus t. If I do that all again for the second system, it has a q lambda, right, equaling lambda plus 2. Set that equal to 0. Solve it. I get lambda equals minus 2. It has a characteristic mode e to the minus 2t, right? That is its characteristic mode. And if I looked at how it releases energy, it's also exponential, but it's faster exponential, right? It decays quicker because it's got that 2 in there. These two systems, both first order differential equations, slightly different Q's, they each have their own characteristic root. That characteristic root dictates what the characteristic mode is, and that characteristic mode tells you the shape, right, of the output and how this system releases energy. If I stuff energy into these systems, right, if I put the same amount of energy into these two systems, I would get these two outputs, right? I would get this output here and I'd get this output here. They would have some similarity in that they were both exponential, but one would be getting rid of its energy faster, right? That D+2 system ends up spitting its energy out quicker. It gets down to zero faster than that first system. So that Q, right, tells us something about the character of the system. In this particular case, the second system has a character of being faster, right? It's a faster system. It decays down to zero faster. It responds more quickly, something along those lines. Okay, we will do a very quick discussion about what happens with repeated roots. I'm not going to go and prove this. You can read the proof in the book, but we're going to go ahead and take a look at this case of repeated roots, and then we'll go ahead and do an example. So if a root, let's do this back in just a regular black. So if a root lambda is repeated r times, okay, what does that mean? That means Q of lambda, right? If you carry out its roots, it's an nth order polynomial, there should be n roots in there, that out of those n roots, r of them are all the same value lambda, right? Something along those lines. Then the solution has a form like the following. It looks like an e to the lambda t, right? And there is an e to the lambda t, but with a t out front. And we're going to keep doing that all the way up until a t to the r minus 1 e to the lambda t. Okay, so when you repeat a root lambda for a total number of r times, so there's r roots lambda, you need r separate independent terms, and the form of these guys are e to the lambda t, te to the lambda t, all the way out to tr to the minus 1, right, e to the lambda t. There's a total here of r independent terms. They would all still have their coefficients. You'd still take a linear combination of them, and you would follow the same procedure. So the lambdas, right? The lambdas come from Q, and they're known, right? Something like that. The coefficients for these characteristic modes, right, are found by the initial conditions. Same kind of procedure. Okay, and so when I do this first example on this, I think we'll be able to demonstrate all of this. So let's go ahead and do an example, something beyond a first order system. So let's go ahead and take a look at the following system. Let's do a d squared plus 2d plus 1 acting on y of t being equal to x of t. Okay, and I want to find y. Whoops. Let's go ahead and find y, zero input response of t. Okay, so I'd like to find the zero input response of t. Because I'm looking for the zero input response, right? Because I'm trying to find, in this particular case, this zero input response, we know that x of t equals to 0. Which implies what? This whole thing goes to 0. We're just setting that equation going to 0. Once we know that the form of the output YZIR is going to be exponential, and it's going to be dictated by the characteristic roots of the system. So I'm going to go ahead and take, in this case, I'm going to go ahead and take Q of lambda, just replace D with lambda. That's going to be a lambda squared plus 2 lambda plus 1, and I'm going to set it equal to 0. That's the characteristic equation. Now, if you couldn't, mentally take the roots of this, you could use MATLAB, you could use a quadratic formula, whatever the case may be. But in this particular case, it's pretty easy to write this out as factored form. It's lambda plus 1 times lambda plus 1. If you FOIL that out, if you expand that out, you get a lambda squared plus 2 lambda plus 1. They're the same thing. So that whole thing equals to 0. This makes the solution pretty easy. We see that lambda equaling minus 1, lambda equaling minus 1. Let's label each one of those. Lambda 1 and lambda 2 are both at minus 1. So this is one of those cases where the polynomial q, this is a second order system, right? The polynomial q is one that the two roots are both at the same location. So I have a repeated root. What does that tell me? That tells me that the y zir of t is going to be some c1 e to the lambda 1 t plus some c2 t e to the lambda 1 t here, because out of this we know lambda 1 is equal to lambda 2, right? Something along those lines. So I could go ahead and write this out as a c1 e to the minus t plus a c2 t e to the minus t. So I know the form of the zero input response. What I don't know are these coefficients C1 and C2. The only way I can get these coefficients C1 and C2 is by having initial conditions. So to find the C1 and C2, we need two initial conditions. Okay? Typically, initial conditions are expressed as what? Well, because they're initial, we're talking the output at time 0, or the output's derivative. All the things are at 0. That's the initial part. So they're usually done things like this. Y at 0 equals something, y prime at 0 equals something, all the way out to y of n minus 1 of 0 being equal to something. There are now n, right, initial conditions. And I know I need n initial conditions because there are n modes to the system. There are n coefficients c that need to be found, that the circuit that is an nth order circuit can support n initial conditions. If your particular circuit did not give you initial conditions expressed as y0 through yn minus 1 all at 0, well, then you would just translate them to those initial conditions using the original differential equation. In this particular case, I'm just going to make some up. I'm going to go ahead and assume that I've got some initial conditions. So I'm going to assume in this case that I have something like this, that I have y zir at 0 being equal to 1 and y dot zir of 0 being equal to 2. So there's two initial conditions. How do I use these initial conditions in order to find those coefficients? So a reminder, my y zir's form, right, was equal to c1e to the minus t plus a c2 te to the minus t. That's the general form in there. What I do is I just throw in the values for my initial conditions. So I know y zir at 0, right, is equal to c1 e to the 0. That's just 1, plus I'm going to get c2 times 0 times 1, which is equal to c1, which is equal to, in this case, just equaling to 1. That's what I had assumed the zir, y zir at 0 was equal to. You don't always, it's only really in the case of repeated roots, get that 0 they're helping you. Usually you would have in this first initial condition an equation in n unknowns. Okay, what we need are n equations in the n unknowns. In this case, n is equal to 2, so I need two equations in two unknowns. It just turned out that that first equation made finding one of the parameters easy. What's the next one? I need y dot of zir. That was the second initial condition. We said that was equal to 2, right? How do I get it? I take the form of my solution, that's c1 e to the minus t plus c2 t e to the minus 2 minus t, and I differentiate it, right? So I'm going to get this whole thing. The first one is going to be a what? I'm going to get a minus c1 e to the minus t, when I just recognized a mistake from my, no I didn't, that's fine. So minus c1 e to the minus t is the first term in there, and then I'm going to get what? I'm going to get a c2 times whatever the derivative of t e to the minus t is. That's a product of terms. I'm going to use the product rule. Product rule says something like this: take a derivative of the first term, t, So derivative of t is just 1, so I'm going to get an e to the minus t term in there. And then I add to that, leave the first term alone, t, and then I'm going to take the derivative of the second term. That's going to give me a minus e to the minus t. So let's make that plus sign into a minus sign. I'm going to get a minus e to the minus t, that whole thing. And I evaluate at what? T equaling 0. So that tells me 2 equals, and I'm going to have minus c1 times 1 plus c2 times, and I'm going to have 1 minus 0 times 1, something like that. And so if I clean this up a bit, and I take a look at these two equations, call this first one up here 1 and the second one down here 2, I get something like this. From equation 1, right, I'm going to get 1 equals c1 times 1 plus c2 times 0. And on the second equation, I'm going to get 2 equals minus c1 times 1, right? And I'm going to have here plus c2 times 1. Two equations, two unknowns. Again, this one, because of that repeated root and because the t terms out there make it easier to solve. If all of the coefficients for the c's that I needed were non-zero, you just set this up matrix style and you'd solve it in the traditional way that you like to solve systems of equations that are linear in those unknowns. In this particular case, I can get it pretty quick. What do I know? I know from equation 1 that c1 is equal to minus 1, right? Just go ahead and solve that. Whoops, not minus 1, plus 1. We can get c equals 1 on that first equation. Once I know that, I can take that and plug it into 2, and that tells me 2 equals minus 1 plus c2. Add 1 to both sides, that's going to give me c2 equaling 3. Now I'm done, right? Y zir of t is equal to c1, which was 1, e to the minus t, plus c2, and c2 in this case is 3t e to the minus t. That is my solution. And it probably is best to say that that's good for t greater than or equal to 0. When we set those initial conditions, it doesn't really make much sense to look earlier than t equaling 0. Okay, so very quick summary then. We are looking at nth order constant coefficient linear differential equations. We are going to break the solution up into two parts, 0 input plus 0 state. The 0 input response is the first one we dealt with. We found out that exponentials naturally solve that equation. If you have an nth order system, you're going to get a linear combination of n exponentials. The shape of those exponentials depend on the characteristic polynomial, solving those for the characteristic roots and then getting the characteristic modes. The strength of each mode, the coefficients out front, how big each one is in the combination, depends on the initial conditions. And you just use initial condition terms to get n equations, n unknowns, and solve for them. If you have a repeated root, you do have to modify the form of those modes to include t times those modes up to whatever the order of the multiplicity is. So you'd get the original one, e to the lambda t, and then a t, e to the lambda t, all the way up to a t to the r minus 1, e to the lambda t. Next time, we will start our progress or our path to trying to find the other half of this, and that's the 0 state response.